Hello everyone, welcome back at the ReThinking NewSpace webinar. I'm Daniel, I'm an AI consultant in the AILab at Fairheart, and here with me today is Niels, also an AI consultant at the AILab at Fairheart. And today we prepared some questions for him regarding the critical role of AI in Earth observation. But before we begin, I also invite our audience to ask their questions in the chat. And then at the end we have a Q&A session and we're going to do our best to answer your questions. So, Niels, what are the trends in NewSpace?
Yeah, so the trends in NewSpace, I think, similar to what our colleagues, previous speakers were saying, we have smaller satellites typically, and we have more of them. So you see more and more constellations of satellites, and these have higher data volumes. But typically, each of these have a bit lower bandwidth, which requires some kind of local processing, although adding these kind of components or AI components to these satellites is still kind of difficult. But that's now like the main trend in NewSpace. And what's also very interesting for us is that data has become commercially available. So it's no longer the case if you want to do something in Earth observation that you need to build your own satellite and send it into space. You can basically just buy your data from providers.
And where can one get this data? What are the sources that one should go to?
Yeah, so there are different sources where you can go. So, for instance, ESA or the US government have their own open data sets that are available. So they provide, yes, you can just go Google it and go on their website and just look up, for instance, I want to know something around my home, and you can just look it up, zoom in on your home, and then just get the data around your home. But yeah, that's only the open data, so you don't have everything. And then there's also restricted data. For that, you can submit like an official request, which is more for like research purposes. So it's if you want to really sell it or create a service to get money from it, it's not very likely that you get accepted. But then you also can buy data. You can just, so there is, for instance, the Copernicus Space Initiative, where you can just go on their website and pay a subscription fee. And then you can get a monthly quota of data, where you can just download your data. And this goes from a few cents per square kilometer to over 50 euros per square kilometer, depending on what data you want. But yeah, you can just go there and buy it. And then the NASA has like a similar setup where you can also buy data. So data is becoming available, and of course you have commercial partners as well that are selling data.
Okay, so let's say we subscribe to a data source, or we just Google some free data. What can we do with it?
Yeah, so what we can do is, wait, the pointer's not working. Okay, so what we need to, we want to automate the generation of insights from this data. So as we get more and more data, it's very important to like quickly get insights from that data. Our businesses are globalized and we are scaling, so you can no longer just go through it manually and just generate your insights by just manually picking and pasting. So if you want to, for instance, know how many solar panels have been installed in your country, you cannot have someone go through all the images and just select all the solar panels. So you want to create an automation of this kind of process. And what you can do, for instance, you can follow up on policies, like I say. You can also follow up on environment. So you can detect forest fires or oil leaks. You can you can police, so you can do law enforcement through that, and you can do urban planning. You can do, there's so many things you can do with this kind of data, and a lot of possibilities that have all been opened up through the automation of all this kind of stuff.
Okay, well, let's say I'm listening to you now and I have a light bulb moment, or one person from our audience has a great idea of like an Earth observation application.
Yeah,
where should we start?
So the first place where I would start is, of course, getting the right kind of data. So there's a lot that goes into selecting your data. So you need to find the right satellite, of course. So there are a lot of things taken into account. So you might be thinking, oh, my application, I need a LiDAR, or I need these spectral bands. So you need to find the right sensor types on the satellite that you want to use. And then you also are thinking about the resolution and flyover time. So how much land should be in each pixel. Do I want something very accurate that is like 30 centimeters per pixel, or can I have like 100 meters per pixel? And also, how many times does the satellite fly over this place? And then, of course, you want, for instance, you might need data over the whole world, or you just want your own country, or you want a specific place. And then when you have gathered all this together, then of course there's also a cost to it. So you need to pay for this data as well. So either you get data, you pay for data that you get commercially, or you need to make like a satellite, or you need to step into some initiative to create a satellite. And then, so selecting the right data, and if you have good data, then you can really start developing your ID.
Okay, once I download some data, what structure should I expect? How does this data look like?
Yeah, so what does data look like? You have each data point, so each data point that comes from a satellite has like multiple values. So you have multiple sensors, and you have multispectral measurements. So you have multiple values that have been measured for each data point. But then you have like, for each data point, you also have locations. So in each location, you have one data point. But you don't have just one data point, so you also have data points through time. So you have, as your satellite passes over the same location multiple times, you get more data points for the same location. And then you get actually also a time series over the whole Earth. And that's like, that's this kind of 3D structure in your data that you then have. Yeah.
Okay, but this looks like a very complex data structure. Are there any challenges you want to talk about?
Yeah, so it's both localized data and time series data have their inherent difficulties of working with it. So working with localized data, you might, for instance, want to efficiently get the data within the country, the borders of a country. It's kind of hard to just go and say, okay, these points are all within my country. But those are problems that have been solved in separate applications. So in like localized applications, like in GPS systems, or like navigation systems, or like at maritime applications, you have these kind of localized data that you already have there, and these problems have been solved. And the same goes with time series data. And so people have been smart, of course, and have combined these together to create very similar, to create these kind of solutions to work with this kind of data. So you have full software environments where you just load in your data. So you download data, you put it in, and then you can start looking up, you can also start asking it questions. You can say, hey, I want within my country, I want this and this and this, and then it returns that to you. But if you want to program it yourself, if you want to get your hands dirty, there are software libraries which also include, which help you work with that kind of stuff. So you have code ready to just ask, get me the data within this location, or get me data from this time, and so on. So there are things there available for you to really work with this kind of data.
Okay, so at this point, I would like to invite again and encourage our audience to post their questions in the chat. And Niels, once we have this data, is this data ready to use, or do we need to process it somehow before we can do something with it? Yeah,
it really depends, right? So there can be a lot of noise in these kind of images. So it depends, like, has the noise already been removed? But if not, you need to do some noise removal. So you have some stray light, you can have smear, dark offset, and so on. Different sources of noise that you want to have removed before you start using it, of course. If you if you are not collecting it yourself, then it might be that your data has not been localized yet, and in that case you need to determine the location and the timestamp for each single pixel in your images that you get, which is basically, if you have like a sort of video over the Earth, you need for each single pixel determining the coordinates in some kind of reference system together with the timestamp. And then one that might be overlooked is that if you want to fuse sensors, so for instance, say that you have this constellation of satellites, and each of these satellites has the same kind of multispectral camera, for instance. You expect them all to be measuring the same thing, and you want to combine that data all together because then you can cover a lot more ground. However, each of these cameras might be measuring in a slightly different way. And if you then just combine that data together, then yeah, you create a disaster, right? So there is this bias between these instruments, and you need to correct for that before you actually go into can start using it, because otherwise your measurements are all over the place, and the results you get won't be true in respect to reality.
And are there tools for doing this, or is this something that someone does manually?
Yeah, manually I wouldn't start doing it, right? So manually it's like an impossible task, I would say. But yeah, AI techniques come to rescue here, luckily. So we have these noise correcting algorithms that do this kind of stuff, remove smear and remove your dark offset noise, and all these noise sources. For labeling your pixels, so for figuring out where each pixel in your image is, there are these very smart algorithms which use like the location of the pixel in your image and the location of your satellite to do a really smart calculation of what the location is of that pixel and just label them. And then to correct bias, we can actually use machine learning. So machine learning can learn this kind of bias between these instruments, and it's very interesting because we do not always know what the source is of this bias, and for machine learning to solve it, we don't need to. So that's very handy, because otherwise we would need to first figure out why is there some bias on these sensors, why are they measuring a bit differently, and what do we need to do to solve for that. But with machine learning, it can just learn that from the data that we gather. So yeah, there are techniques that help us to do this.
Okay, so now we have the data, we have the tools to pre-process our data. Is this enough, or do we need something else to start actually using our Earth observation data in some application?
That highly depends, right? So probably, for instance, let's go back to the example where you want to count how many solar panels there are, for instance. Then, yeah, to learn that, you probably select some kind of supervised algorithm. A supervised algorithm, of course, needs labeled data. So example data, you need to show it what it needs to do before it can do something for you. And this requires you to just go through the data that you have and just start pointing and saying like, oh, this is a solar panel or this is a solar panel. Similarly, when you want to, for instance, determine the amount of greenhouse gases in the air or something like that, you need to make manual measurements and show the algorithm. Yeah, okay, this is your data that you get, and this is the measurement that I made. And now you need to find the relation between the two. And once you know the relation between the two, I can use the algorithm to do it for the whole Earth. And then, yeah, of course, this kind of data is not easily available because it's very time-consuming and very expensive to create. If you want to go around the world and start measuring stuff and over time even, and then you need to correlate it to the satellite that has been measuring, then, yeah, of course, that's very expensive to do.
Okay, so this is clearly a limitation here. Are there any better solutions?
Yeah, in some cases you can actually formulate your problem in a different way, and in a different way I would say, you can use some unsupervised approach maybe. So what this means is, so for instance, let's say you want to determine the sources of dust in the air, so some dust storms that are starting. You want to know where are they starting, where is this source of dust in the air. What you can do is select the interesting wavelengths for these kinds of this kind of data. So in this case, what wavelengths have information on the amount of dust in the air, for instance, and then you apply like a clustering algorithm and just cluster the globe in like 1,000 classes or something, which means that the algorithm will just divide the world in 1,000 classes, 1,000 similar classes. Each object in each class is similar to each other. So it will say, oh, this patch on the Earth is similar to this patch, and this patch is similar to this patch. And then you need to manually, of course, determine what each cluster means, so what each class means, and then if you can find the class that corresponds to a dust source, then you have your system ready, and then you can just start running it. And once it's running, then you can generate value because you know where these clusters are, because the clusters are automatically generated.
That's a really good approach, but is it enough? For example, if I want to predict some values in the future?
Yeah, so once you start needing to have values or you want to do something towards the future, then it might become more difficult to use unsupervised approach, and you want to have actually train these things with supervised data, so with labeled data. And then you can but you can still leverage your unsupervised algorithms. So what you can, for instance, do if you are in the Arctic shipping business, you can have these, you want, for instance, a routing algorithm that avoids thick ice in the future. So you need to predict where thick ice will be in order to avoid it beforehand. What you then can do is you can use an unsupervised algorithm to label like the ice, to create different clusters, and then you need to see what does each cluster correspond with. Does it correspond with like open water or like patches of ice or really thick ice? And then you can use that algorithm to like label your data for you. And then you have labeled data that you can use for a supervised algorithm. And in that sense, you are still using a supervised algorithm, but you do not need to label a lot of stuff yourself manually. So I think that's like a nice way of like avoiding having to spend a lot of money to just label all the data that you have.
Okay, so far it seems that labeling itself is quite a difficult challenge for Earth observation data. But in many other fields, we can already find a lot of data which is already labeled, like with animals, with cars, with people even. Is it not the case with Earth observation data?
So with Earth observation data, the difficulty is in that it is very expensive and time-consuming to create these kinds of data sets. So what you actually need to do, so if you want to create this kind of data set, you need to make manual measurements. So you need to go measure whatever you need. So for instance, if you want to measure the amount of a certain greenhouse gas in the air, you need to make manual measurements of that amount. And you cannot just do it. You cannot go just outside the office and just say, "Oh, I make some measurements and I'm ready to start making creating some value through like an algorithm." No, you need to go around the world, or need at least different places in the world where you make measurements, and you cannot just then go, "Oh, I make a trip around the world and I just make some measurements everywhere." That's not really possible. You need to have measurements through time also. So your measurements need to be spread through space and time. And what's very important is that you have measurements through different circumstances. So if you only look at the weather, there is already a lot of different things that can happen. It can be sunny, it can be raining, there might be a storm, it might be snowing, and so on. And you want data from all different in this variance, you want in all different circumstances you have data in order to have like a good algorithm that works across the globe or across the area where you want it to work, of course. This is very expensive to create. So companies that did this, they have these data sets available and they are generating value from it. They do not really like to share this data, of course. Why would their competitor be allowed to generate value for themselves? However, there is like this call for open data, so there are some organizations that are calling for making this data available for the public in order to like drive the innovation, right? So this also happened in the maritime industry where they already went through this, and they by making these kinds of open data sets available and really accessible for the public, then these smaller companies and really the like startups have like these bright ideas and they can do something, because now it's too expensive for them to really start doing something. And I think that is very interesting to keep an eye out for, even if you are not looking into this or saying like, "Oh yeah, I do not want to do anything with this, or I do not want to make my my data sets public, it might be interesting to see once these data sets start to become available, there will be a lot of opportunities and there will be a lot of things going on and a real boost in innovation and everything that is being created. And then it might be interesting to jump onto that wagon on when it leaves on the train when it leaves the station, because otherwise, you'll get behind, right?
Niels, thank you very much for answering my questions. Now it's time to answer a few questions from our viewers. So, the first one would be, how does AI prepare the daily upcoming usage of quantum technologies? And are you working on it at the AILab?
Right now, we're not really doing anything with quantum technology. Of course, it's something that's upcoming, but I think it's still, in practice, it might still be a bit longer way off. Just because it's very expensive, very difficult to get these quantum technologies and get them up to speed with what we do. And we see that there is still a lot of requirements to just use the deep learning and even the standard machine learning algorithms or just algorithms in general. There's a lot of digitalization still happening and there is still a lot of value being created. So I think quantum is maybe a step further than that.
Okay, so this next question. What particular AI solution for inter-instrument bias are there? How to design it?
So what you, for instance, can do, if you know these measurements and these measurements should be the same, then you can start, you can make, for instance, a sort of deep learning regressor, or you might make some support vector machine, for instance, that tries to find what do you need to do to make these align with each other and bring these in line. And then in that way you can create something. Of course, it can be difficult to really figure out what works best and what can help you the most, and then it's really specific to the problem that you have and the case that you want to make.
Okay, and the final question for now. How do we guarantee the reliability over the life cycle of the algorithm?
Yeah, so I think it's very important that you just enter good data into it. In principle, the algorithm itself will keep running okay. Of course, if you are running it over a long time, you might want to have some continuous improvement going on, so that you are that you are retraining your algorithm on new data that you collect, so that you continuously get new data. This doesn't have to be really much, but you can get more data. You can also put quality metrics on the data that you are gathering, and in that sense you can get more and more data to keep improving your algorithm, so that your algorithm moves with the changing situation of the Earth, for instance, or whatever you are measuring.
Okay, thank you very much, Niels. Thank you, our audience, for joining us in the critical role of AI in Earth observation. Now we're going to hand over the stage to Olivier for closing off this webinar. Thank you.